Unit Operation Classroom, GATE 2023, question 29. For a fully developed turbulent flow, incompressible Newtonian fluid through a pipe of constant diameter, which of the following statements is or are true? So, this is talking about Reynolds stats, average velocity, so and pressure gradient. So before that, let's quickly see what is turbulent flow and Reynolds stress. This is going to be a very quick summary of and just we'll discuss whatever exactly is required for answering this question. Very simply, we know in the laminar flow is smooth ordered layers the flow inside a pipe, and for a turbulent flow it's a very chaotic, swirling, unpredictable motions. So if this is a plot of the velocity versus time, you see this is a constant fluctuation, and this is the fluctuating component u prime. Okay, so the actual velocity is the mean velocity plus the fluctuating component. And let's say this is the fluctuating component in this direction, and the fluctuating component v prime in the transverse direction. So, and that is actually responsible for the transport, any transport of the momentum from one layer to the other layer. Okay, so formally, we can say in turbulent flow at any point inside a pipe, the velocity is not constant in time. It fluctuates around a mean value. So we can write this one as this is ut is the instantaneous velocity in streamwise direction. Let's say this is flowing in this direction. So this u bar and a over bar and v over bar are time averaged velocity, steady mean flow. So this is the steady mean flow time average plus this is the fluctuating component, and vt is the instantaneous velocity in the transverse direction, in this direction if this is the flow in this direction, perpendicular to the flow in the y direction. Again, that's the mean velocity plus the fluctuating component. Okay, and of course we are talking about the Cartesian coordinate. For a pipe flow, for the streamwise velocity, let's say if this is a direction here, they use a t, or force is equal to the mean velocity plus the fluctuating component, and in the radial direction. So we're talking about a pipe here. In the radial direction, so again the mean velocity plus the fluctuating component. And mean velocity, of course, radial velocity of this is going to be in fully developed flow, but the fluctuating component is not going to be equal to zero. So these are, of course, these primes are the fluctuations in the z and r directions. So what is Reynolds stress? Reynolds stress is, of course, an extra stress due to turbulence. In laminar flow, this we know from the Newton's law. Everybody knows about it. But in turbulent flow, we add another term, which is the viscous stress, and there will be a turbulent stress. What is the turbulent stress? Say these are the fluctuating components, and of course, the fluctuating components have mean over the time, and the velocity, and in the transverse direction over the time is going to be zero. But when you take the average of the product of this two fluctuating components, it's not equal to zero. It's not zero, and this is a negative quantity, and of course, it's called stress. So here, this is the momentum transport, the shear stress component of that. Okay, so what are the key facts? Just take away at the wall of the pipe right here, at the wall of the pipe here, uh, that means that R is equal to R, no slip condition. At the no slip condition here, this velocity is going to be zero, and radial velocity is going to be equal to zero, and so this is going to be equal to the fluctuating components, of course, over the time that's going to be equal to zero, and in fact the Reynolds stress is going to be also equal to zero right at the wall. So these are all the conditions that's true at the wall. These are all components of zero. But at the wall, only the viscous shear stress remains. So at the here, this is the maximum, of course. Viscous shear stress remains, and it's maximum compared to other locations in the pipe. So, but what happens at the center line? We looked at the wall. Now, what happens at the center line? At the center line, these are, of course, is going to be zero. This shear stress component, shear stress component is equal to zero at the center line. But other components of the Reynolds stress tensor, that means in the other directions of this fluctuating components are not equal to zero. That, of course, is not, we are not going to think about that in relevance to this particular problem. So Reynolds shear stress, remember there's a negative quantity here. This is Reynolds shear stress is zero, both at the wall. So this is going to be zero at both at the wall and at the center line, right? Both at the wall and at the center line here, this Reynolds shear stress is going to be zero, but turbulent fluctuations are normal stress at R is equal to zero are non-zero. So, if I just take a very quick summary, what would be the Reynolds stress value at the wall? That is zero, at the center line zero. So this is my wall, this is my wall, and this is my center line. At the center line zero, at the wall is zero, but near the wall, but near the wall it's kind of small, and in the buffer region after that, it's the maximum. So let's look at the options one by one. Okay, first option, it says demonstrates average over a sufficiently long time is zero everywhere inside the pi, and as we can see, that's not true. Okay, at the wall it's zero, at the center line zero, but here these are not zero. So option A is false. Let's look at option B. Reynolds stress is at the pi wall is zero, and we have looked at that is of course true. Okay, average velocity of the fluid is half its centerline velocity in a turbulent flow. That's true for, of course, laminar flow, but for a turbulent flow, we know the average velocity. So this is a very kind of flat profile, and the average velocity is around 0.8, depending upon the value of the Reynolds number. But it's very close to the centerline velocity, the average velocity. And the average pressure gradient, the flow direction is constant. Of course, that's also going to be true. So option A is false, and of course, option C is false. Again, option B and option D are true. Right? Okay, now let's quickly see what would be the implications of this problem in process design. We know normally we take the collector the lab scale data, and that is scaled up. So in the lab scale, the flows are usually laminar, but in the actual plant scale, they are turbulent. So we have to remember that, and the Reynolds stress factor must be accounted for in terms of velocity profile and the pressure drop calculants, and that of course influences the heat transfer coefficient and then the heat flux calculations also.